Hi, hello everybody. So in today's session, we are going to start with the second theory from coordination complexes, that is crystal field theory. Please write the heading, crystal field theory. Okay, so in the previous session, we have been discussing about the valence bond theory, wherein we discussed that if you have a metal which bonds to the ligands, and we said that it is completely covalent, and we also discussed certain examples of how to predict the hybridization, how to predict the number of p-pi, p-pi, and p-pi, d-pi bonds. Everything was discussed. Okay. Now, there are certain limitations of VBT. Okay, so write down the next point. Limitations of valence bond theory. That is the reason why we needed another theory to explain it in a better way. So, the first point was please note it down, could not explain the nature of strong field ligands and weak field ligands. So we said that the pairing of the electron happens because of the nature of the ligands, and they can be classified into two, either strong or weak. But then VBT was not able to differentiate between strong and weak ligands. Okay. And next, why pairing occurs? Why pairing occurs when strong field ligands are bound to the metal. Okay, that was also not explained by VBT. Now, the third one is could not explain distortion in complexes. Could not explain the distortion of complexes. So in this theory, we are going to address all these demerits of valence bond theory. We'll be discussing about what are the differences between strong and weak field ligands. When you have a strong field ligand surrounding the metal, how come pairing is happening over there? And there are certain complexes which shows distortion in their structures that will also be discussed. Okay, so these limitations are addressed by the crystal field theory, also called CFT, crystal field theory, or CFT. Okay, so here what CFT says is there is no concept of hybridization. Unlike valence bond theory, wherein we discussed about a lot of hybridization. Octahedral can have D2, sp3 or sp3, D2. Trigonal prism can have D5s. Similarly, tetrahedral can have a set of hybridizations. So no such hybridization of the concept of hybridization was applied over here. Okay, so no hybridization meaning there is no overlap. No overlap of atomic orbitals, no covalent bond. This was not the concept of crystal field theory. Okay, while crystal field theory was entirely dependent on electrostatic forces of attraction between the metal and the ligand. So unlike VBT, where everything was explained on the basis of hybridization, on the basis of the formation of a covalent bond, here there is no hybridization. It's all about electrostatic forces of attraction between the metal and the ligand. So usually what is considered is you have a metal. Metals are usually considered to be the positive charge. Okay, metals are usually considered to be the positive charge. And you have ligands, for example, fluoride, it's a ligand, which is negative in charge. So there is an attraction between the positively charged metal and the negatively charged ligand. So can you see there is an electrostatic force of attraction between the metal and the ligand because one is positively charged and the other one is negatively charged. And this is the concept behind crystal field theory. So you can see metal is a kind of ion, it's a cation. Ligand is also a kind of ion, which is an anion. And what you can see over here is ion-ion interactions. Correct? What you can see is ion-ion interaction. So this is one case where the ligand is negatively charged. Now you can have species where it is not negatively charged, but let's say you have a metal, okay, which is positively charged, and then you have a ligand like water, which is neutral, or ammonia, which is neutral. So they have a lone pair of electrons, but we already know that oxygen is way electronegative than that of hydrogen. So this will carry a delta minus and this will carry a delta plus charge. Correct? Delta minus, and over here metal is positive. So this positive and this negative over here will show electrostatic forces of attraction, and hence this kind of interaction between the metal and the ligand is called, this one over here is a ion, that's an ion. Over here it's a dipole. Correct? It's a dipole because the electrons are shifted towards the oxygen. It creates a dipole. So this is ion-dipole interactions. Ion-dipole interactions. So this is the way how CFT puts its theory. It's not about covalent bond. What it says is it's all about electrostatic forces of attractions between the metal and the ligand. And while explaining, you can see that whenever it explains, it considers the metal to be static in one position. Metals would be fixed in one position and the ligands would move towards the metal. So the positions of metal, that is considered to be static, and the ligands are considered to be dynamic. Ligands are considered to be dynamic. Okay, so this is how it is. Also, when you have a crystal structure, you have any crystal structure of a coordination complex, there the metal occupies the voids while the ligands occupies the lattice points. Generally, most commonly, this is how the structure of any crystal structure of a coordination compound looks like. Okay, so metals are usually static, occupying the voids, while to form the crystal structure, the ligands are dynamic, and finally they occupy the lattice points. Okay, so this is how it is. These are some of the very basic postulates of crystal field theory. Now what you have to learn is you have to learn how crystal field theory explains the splitting of the d orbitals. Very important. So write down the next heading, crystal field splitting in octahedral complexes. Very important, very important. Crystal field splitting in octahedral complexes. Okay, so please pay attention to each and every word. Okay, so now let's say that you have a metal which is free. Okay, you have a metal which is free. Now we know that metals who actually form these coordination complexes do belong to the transition block elements and they'll be having the d orbitals. So we are concerned with the splitting of d orbitals. We are concerned with the splitting of d orbitals. Okay, so when the metal is in free state, this is metal in free state. So when the metal is in free state, which is stage 1, where there are no ligands surrounding, just the metal. Metal is free. So in that case, all the 5 d orbitals of the metal would be degenerate. They would be degenerate. Now, the moment you have a metal and there are ligands who are approaching the metal, they have not formed the bond, Please pay attention. They have not formed the bond. They are just approaching the metal to form the bond. So when they approach, they will come closer, 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 like this. Okay, so they are coming closer, closer, closer to form the bond. And the moment these ligands come closer to the metal, what happens is the energy of all the 5d orbitals rises. It rises. So this is where there is a symmetric ligand field. Symmetric ligand field. What does that mean? That means you have a metal at the center and symmetrically the ligands are approaching the metal closer, 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 closer to form the bond, to form the coordinate bond. Okay, here there is no concept of coordinate bond. It's just about attractions, whatever. So to form the complex, the ligands are approaching in a symmetric manner. And this is stage 2. This is stage 2. Now, when you have ligands approaching the metal, why is the energy increasing? Okay, so this is my axis of energy. As we move up, the energy increases. Now, you can see that from stage 1 to stage 2, the energies have increased, correct? The energy has increased of all the 5 orbitals. All the 5 orbitals have increased the energy. Why? Why? Because understand that the metal has a certain set of electrons, correct? Metals will have a certain set of electrons. And when you have ligands approaching them, ligands come with a pair of electrons. We already know that. The function of the ligand is to donate a pair of electrons to the metal. So they'll also be coming with a pair of electrons. Now you can see electrons on the ligand, electrons on the metal. So in the free state, the metals are very free with the electrons. But then when you have a symmetric ligand fields, these lone pair of electrons interact with the metal and there would be electron-electron repulsions. Electron-electron repulsions. And when you have, are electron-electron repulsions stable? No. Correct? So it is because of the electron-electron repulsions between the metal and the ligand that the energy of stage 2 is higher than stage 1. Okay, if you want to write it down, please write it down. Stage 2 arises due to electron-electron repulsions between the metal and the ligand. Also, it could be due to the nucleus repulsions as well. Correct? Metal will have nucleus with protons. It is positively charged. Ligand will also have a nucleus with protons. So positive and positive repulsions can also happen. So it could be due to the electron-electron repulsions or the nucleus repulsions that causes the rise in the energy at stage 2. Now, when the ligands have finally formed a bond, when the ligands finally form a bond, here these 5 orbitals will no longer remain degenerate. Instead, they will split into 2. I'll explain why. 2 at the top, 3 at the bottom. Very important. 2 at the top and 3 at the bottom. And these orbitals which goes to the top and which comes to the bottom are very important. The ones that go to a higher level is, correct, going higher in energy are dx square y square and dz square. Okay. While those that come lower in energy are dxy, dxz and dyz. And the center, the exact center between the two, it's called the barycenter. It's called the barycenter, which is the midpoint. 2 of them goes up, 2 of them goes down. No, two of them goes up, three of them goes down, and the center is called the barycenter. The center is called the barycenter. Okay, now let me try to explain why dx square, y square, and dz square have gone up and the others have gone down. Okay, let's try to understand. Now consider a metal. Okay, now what I am imagining is this is my xy plane. Suppose this is my xy plane, and above this plane, which I'm showing with a wedge bond. So this is my x. Along this, I have my x. Along this, I have my y. Towards the top, I have my z axis. Okay. And towards the bottom, this is minus z. Okay, now the way a octahedral complex looks like is you have a central metal. There are 4 ligands in the xy plane, and there are 2 ligands along the z-axis. Correct? 4 ligands in the xy plane. I want you to imagine in a 3-dimensional space. Okay? So here, the central metal atom and all the 4 ligands, they lie in the same plane, xy plane. And then you have a ligand which pops up, pointing up, which is in the plus z direction. And there is another ligand which is popping down, minus z axis. This is how it is. Okay. Now, when you see the overlap of the ligand with the metal, important, when you see the overlap of the ligand with the metal, we can see that it is approaching axially. It is approaching axially, meaning if I have to draw the dx square y square, okay, let me just explain the 5 types of orbitals before so that you can understand. Okay. So if you have, let's say dxy, so you have x, you have y, and dxy means the lobes of the d orbital will lie in between x and y. Correct. Now, for the sake of simplicity, I'm just pasting it again. Now, let's say it is xz. If it is xz, then the lobes of dxz will lie in between x-axis and z-axis. If it is yz, the lobes would lie between y and z-axis. So these are called the non-axial orbitals. Non-axial d orbitals. While there are axial d orbitals, axial d orbitals. That means they lie in the same plane. For example, if you have dx square y square, then it would lie like this. This is x-axis, this is y-axis. It would lie like this along the axis. Along the axis. See, this is how it is, along the axis. Okay, while if you have dz square, let's say, this is z-axis. dz square is represented like this, along z. Along z. So this is dz square. So these are the 5 types of orbitals, 3 non-axial and 2 axial. Why is it called axial? Because the lobes are directed along the axis. Lobes are directed along the axis. Okay, so if you can see a octahedral geometry, there the ligands approach through the axis. Please pay attention. If I have to draw, let's say, let me draw a cube so that you can understand. Okay. Now, okay, let's say this is the case. Now try to imagine this. Okay, this is our cube and I have a central metal over here. Let's say this is my ligand over here, one ligand backward, one ligand forward. And you have one ligand at the top, one ligand at the bottom. Please imagine it in a 3D space, okay? So you have a left face and you have a right face, at the center of which you have two ligands, correct? You have a front face and a back face, at the center where you have two ligands, and you have a top face and a bottom face at the center of which you have a ligand. Correct? So if I have to draw the axis, if I have to draw, let's say dx square y square, see? This is how it is going to be. This is my dx square y square. Dx square y square. So can you see the ligands are approaching through the axis. Now if I have to draw dz square, this is my dz square. This is my dz square. I hope you can imagine it. Dz square. So when you have ligands approaching to form an octahedral complex, the ligands approach through axial orbitals. Please note it down. Please do not by heart this. Please do not mug up these concepts. Understand. Because we have a lot to mug up. So I'll tell whatever you have to mug up, you have to by heart. Over here, understand the concepts. Okay. So to build octahedral geometry, what will happen? The ligands approach the metal center along the axis, along the axial orbitals. Who are the axial orbitals? Axial orbitals are dx square y square and dz square. Correct. As a result of which, the ligands come with a lone pair of electrons. Metals already will have electrons. So the electron-electron repulsions along the axis will increase. I am repeating it. Ligands will come with a lone pair of electrons. All the metals will already have electrons in it. So the electron-electron repulsions are increasing along the axis because that is the way the ligands are approaching. So if the electron-electron interactions along the axis are increasing, the energy of the axial orbitals will increase. Okay. Now, how much ever increase is happening, the same extent of decrease will happen to the other three. Okay. So this has increased, let's say, by plus x units. As a total, the other three will decrease by minus x units, always. So the increase will be compensated by corresponding decrease. Now, how much increase is there? Corresponding to each of these. Or let me say this first. Okay. This splitting from this point to this point, this is called crystal field splitting energy. Crystal field splitting energy. Delta O is crystal field splitting energy. Please be careful. Lot of students make mistake over here. I'll tell you how. So the separation between whoever has gone up and whoever has come down, the separation is notated by delta O. O stands for octahedral geometry and that is crystal field splitting energy. Okay. Now the extent or the energy difference from the center to the top, that is also important. So this much is minus 0.6 delta O. And when you come to the bottom, it is, sorry, this is increasing, plus 6.6 delta O. And to the bottom, it is minus 0.4 delta O. Write it down. Okay, so delta O is the total crystal field splitting energy. Now, each of the orbitals which has gone up, it is also known by another name. It's called EG. And the bottom ones are called T2G. Why E? Because it is doubly degenerate. Here it is termed as T because it is triply degenerate. Okay, so what I'm going to write over here, each of the EG orbital is destabilized. Please pay attention to my words. Each of the EG orbital is destabilized. Why am I telling it is destabilized? Because it has increased in the energy. Correct? Because it has increased the energy. Increasing energy is decreasing stabilization. Energy and stability are inversely proportional. So each of the EG orbital, each EG orbital is destabilized by 0.6 delta O. By 0.6 delta O. So plus sign means destabilization. While T2G, each T2G orbital is stabilized. Why is it stabilized? Because the energy is going down. It's stabilized by minus 0.4 delta O. Important, important. Okay. So can you see 2 of the orbitals have gone up, meaning 2 into 0.6 delta O is the destabilization energy, while 3 has come. So this is equal to 1.2 delta O. Okay, while 3 of the other orbitals have gone down. So each of the 3 has got minus 0.4 delta O. That is 3 into minus 0.4 delta O, which is minus 1.2 delta O. So if you sum up, can you see it is 0? That is what I said. The amount of energy which is being destabilized by the 2 orbitals is compensated by the stabilization by the 3 orbitals. Okay, so plus sign notates destabilization, minus sign notates stabilization. Plus destabilization, minus stabilization. Okay, now we'll be filling electrons and we'll understand it. We'll take it slow. So this is how the splitting occurs in octahedral geometry. It splits into T2G and EG. T2G at the bottom, where it releases an energy of minus 0.4 delta O, and it EG destabilizes by 0.6 delta O. Okay, so this is crystal field splitting energy. Crystal field splitting energy. Okay, now let's understand the crystal field splitting in tetrahedral complexes as well. Write down the heading. Crystal field stabilization. No, not stabilization. Crystal field splitting in tetrahedral complexes. Okay, so the initial stories are the same. You have a metal in the free state, which is stage 1, where there are no ligands surrounding the metal and all the 5D orbitals are degenerate. Once you have a ligand symmetry, so in tetrahedral you will have 4 ligands, correct? So all of the 5 will increase the energy and move to stage 2. That could be due to electron-electron repulsions as well as nucleus-nucleus repulsions. Now, when your ligands form the complex with the metal, splitting occurs. Correct? Splitting occurs. And here when the splitting occurs, 2 orbitals come to the bottom, which is labeled as E, and 3 goes to the top. It is the opposite of octahedral. In octahedral, 3 went to the bottom, two went up. It was labeled as T2G and EG, where G stands for gerade. G stands for gerade. Gerade means it has a G stands for gerade. Gerade means it has a center of symmetry. Center of symmetry means, let's say you start from the center, you go up, you see a ligand. You come down, see, you see a ligand. Okay. Now over here, you go to the right, you can see a ligand. You go to the left, you can see a ligand. This is what is meant by center of symmetry. So center of symmetry is there, and hence with the names of the orbitals, you add G. So octahedral complexes do have center of symmetry, and hence EG and T2G. Here, there is no center of symmetry, and hence you don't have to give that subscript of G. It's called E and T2. E and T2. But the thing that you have to be careful of is here also there is a center, which is called the Barry center. The extent of destabilization is going to be the extent of stabilization, just like the earlier case. Okay, it does not look the same. Let me make it same. Okay, now it's better. Okay, now the extent to which this goes up. Now again, here there is a splitting. The splitting is called crystal field splitting energy of tetrahedral complexes, delta T. Delta T it is. Crystal field splitting of tetrahedral complexes. Splitting. Okay. And the extent to which this goes up is plus 4 delta T. And the extent to which this goes down is minus 0.6 delta T. Earlier it was all about delta O because it was octahedral. Now it is tetrahedral. Okay. Now which are the orbitals that goes up? dxy, dxz and dyz. While the ones that go down are dx square, y square and dz square. Why? Why? The reason is simple. The reasons are to form the tetrahedral complexes. Note it down. To build tetrahedral complexes, the ligands approach nearly to the non-axial orbitals. Nearly to the non-axial orbitals of the metal. Okay, so in the earlier case, we saw that the metals, when forming a bond with the ligands in octahedral complex, they were interacting directly with the axial orbitals. Axial. But here it is non-axial. Here it is non-axial, and these non-axial orbitals will hence increase in energy due to electron-electron repulsions. 3 non-axial orbitals, all of which will increase then. I'll just show how it looks. I'll just show how a tetrahedral looks inside a cube so that you can imagine. Okay. So if you have a metal, okay, the way it will look is, let's say you take this corner and this corner of the top face. Okay. Now to form a tetrahedral complex, it will take the opposite corners of the opposite face, meaning this corner and this corner. This is how it forms. This is a tetrahedral complex. This is how a tetrahedral complex looks like. So if you can see, none of the ligands are coming through the axis. This is x-axis, no ligands. The top face is the z-axis, no ligands. And the front face is the y-axis, no ligands. Everything is directed towards the corners, non-axial. So that is why here the ligands approach non-axially. As a result, the non-axial orbitals will increase in the energy due to electron-electron repulsions. So here it is destabilized by plus 0.4 delta T and stabilized by minus 0.6 delta T. Okay. All right. So I think it is clear. Learn the concept of the crystal field splitting very, very, very thoroughly. And the next session, we'll be discussing about the factors that affects the crystal field splitting. Please write this delta T is the crystal field splitting energy in tetrahedral complex. Okay? Earlier it was crystal field splitting in octahedral complex. Crystal field splitting energy of octahedral complex. Okay. All right. Okay, so see you in the next.